Okay, so today we are going to be discussing linear algebra. Linear algebra entails the use of matrices. Matrices describe systems of linear equations. Matrices are usually denoted as boxes of numbers, and these boxes of numbers can be square, they can be rectangular, they can be a single row. So for example, a square matrix is a matrix that has the same number of rows as it does columns. Square matrices are very important in linear algebra. A vector is usually known as an n by 1 matrix in that it only has one column and has n rows. But of course, it can also be denoted as a row and n columns. Rectangular matrices are matrices that have a different number of rows and columns. So we can have a triangular matrix. A triangular matrix is a matrix which has in the upper triangle of the matrix all numbers, and in the lower triangle it has zeros everywhere else. Conversely, a lower triangular matrix has numbers in the bottom left of the matrix, and in the upper right all the numbers are 0. The identity matrix is an extremely important matrix in linear algebra. It's a square matrix that when you multiply by any matrix, it gives back that other matrix. So for example, the two-dimensional identity matrix is going to be 1, 0, 0, 1. The three-dimensional identity matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So we have ones along the diagonal. So in case you're asked, we denote big I sub n as the n by n identity matrix. To discuss a little bit of matrix notation. So each element of a matrix is given a certain index. So for example, in this matrix here we have on the top row A11, A12, A13. So the small 1 after the A denotes the row number, and then the small 1 after that small 1 denotes the column number. So for example, A13 says that it's the number in the first row and third column. A32 is in the third row, second column. A diagonal matrix is any matrix that has no numbers in any position bar along the diagonal. The transpose of a matrix involves flipping all the numbers across the diagonal. So here we have a 2 by 2 square matrix. We have 1, 3, 2, 1. The transpose of that involves flipping the 2 and the 3 across the diagonal. So that leaves us with 1, 2, 3, 1. For example, if we had a 3 by 3 square matrix, if we had 1s along the diagonal, and we say we had 2, 2, 3, like so, and 4, 4, 5, like so, the transpose of this would be like so. 1s along the diagonal, yet we flip everything on this side over to this side, and flip all of these here up onto the top. So this now becomes 2, 2, 3 on the bottom, and 4, 4, 5 along the top. So a transpose matrix just mirrors across the diagonal. So a quick explanation of what is actually happening with these matrices. So usually we denote a matrix to describe some multiplication by a vector, and this equals some other vector. So back when we did algebra, we have systems of linear equations which we can solve if they're all simultaneous. So if we have 3 variables, we can solve using 3 different equations. If we have 2 variables, we can solve using 2 different equations. This is similar to how matrices work. So on the left, we have a matrix A multiplied by a vector x, which is equal to some vector b. So what we have written here is the same as writing x1 here plus x2 here equals 4 over here. We also have x1 minus x2 equals 0. Well, that's a fairly simple simultaneous equation to solve. We have x1 equals 2 and x2 equals 2. So, as we did back in previous examples, we have x, y, z as the variables, but in linear algebra, we can't have matrices large enough that there aren't enough letters to describe what we're talking about, so usually we denote it as x sub a number. So again, over here with a 3x3 matrix, we have a times x1 plus b times x2 plus c times x3 equals 1, and so on the whole way down. D times x1, e times x2, f times x3. So you can consider a matrix multiplied by some vector, assuming the vector is full of variables, as some system of linear equations that we can solve in the same way we would have solved simultaneous equations in algebra.